is Level 2 Chemistry, the 2025 exam 91164. Demonstrate understanding of bonding, structure, properties, and energy changes. So I'm going to go through the whole exam. I'm going to use, if I can help it, the resource booklet that's provided, and also use the calculator, which is most commonly used by New Zealand students. So with that said, let's do it to it. The first question is a kind of slightly odd one. It says that sodium chloride, NaCl, is used as an antiseptic and antimicrobial agent. It's table salt, so hopefully you know that NaCl is just table salt. So why they need to tell you that, I don't know. But anyway, in analytical chemistry, it is often reacted with silver nitrate, AgNO3, shown below. When silver nitrate, AgNO3, is added to 73 grams of sodium chloride, 81.8 kilojoules of energy is released. Calculate the change in enthalpy reaction enthalpy for the above reaction, and it states there that the molar mass of salt is 58.4 grams per mole. So the first thing that should be popping up in your head is to go to the formulae, and you'll see this formulae in your formula sheet. And bad news, it's a trap. You will not be able to find the answer using this equation, but you will be able to find it if you know what enthalpy of reaction actually is, and it's the energy change per mole of the reaction. And they give you more than enough information here to be able to solve this. So first thing we need to know is we need to know the number of moles of NaCl. All right, and we're told that there are 73 grams of the sodium chloride, and that the molar mass is 58.4 grams per mole. So this is going to be little m over big M question. So this is going to be 73.0 grams divided by 58.4 grams per mole, and that's going to give us how many moles there are. So let's get out of there. So 73 divided by 58.4 is 1.25. So 1.25 moles of sodium chloride. All right, now we are told that 81.8 kilojoules of energy is released when we do this reaction. So remember that enthalpy of reaction is defined as the energy change per mole. And you see there per, so you're going to be dividing something. So you notice that there were 81.8 kilojoules of energy, and this was done by 1.25 moles of sodium chloride. So what is the kilojoule per mole? Well, let's clear that one out. So it's going to be 81.8 divided by 1.25. So 65.44 kilojoules per mole. And that's it. That's how you would do it. So again, yeah, it is a trap. Next, we're asked to identify which substance below matches the information provided in the table by placing it in the correct row. Zinc, which is a metal, ammonia, NH3, diamond, crystal carbon, and sodium chloride, salt. Okay, this should be a fairly easy question. This is obviously diamond. Diamond is a 3D covalent network. This is going to be sodium chloride, NaCl. There's only one pure metal in there, and ammonia, NH3 should be there. It's a molecule, 1 nitrogen, 3 hydrogen. Yeah, it just is. I mean, you should know that zinc and salt and diamonds do not melt at -78, so it's pretty easy to put that one there. Now we're asked to relate the bonding and structure in ionic and molecular solids to their relative melting points. In this answer, describe the bonding and the structure in ionic and molecular solids. Explain what the melting point of a solid indicates for about the strength of the forces between the particles, and link the strength of forces between the particles to their relative melting points. Okay, well, ionic solids such as NaCl and the molecular solids, that would be a molecular solid is solid ammonia at a really, really low energy rate. Okay, let's just compare that. So let's look at the bonding and structure of these molecular solids. So let's have a look at the sodium chloride first, I think. So this is an ionic lattice. So it's a 3D lattice, and it's held together by combining sort of positively charged cations next to negatively charged anions. So remember which one is which from memory. So that's why they would have a really, really high melting point. The reason being is that when you have a lattice like that, it takes an awful lot of thermal energy going into this molecule in order to break them up, because the thermal heat has to overcome those bonds. Let's compare that with the molecular solids, and the molecular solids that were given there were ammonium. So these are just individual molecules. They're just individual molecules that are just held together by intermolecular forces, and these are much, much weaker than the electrostatic lattice forces that are holding the sodium chloride together. So it has a melting point of minus 78 degrees Celsius, which is going to be about 160 Kelvin, I think. We're around about, just doing the maths quick in my head, which is really, really cold. So it doesn't require much thermal energy to enter the molecules to break those molecules apart. And the molecules are going to stay together, but the forces between those molecules are what we're really talking about. It's not going to take much to overcome those at all. There's no big link. Whereas the sodium chloride, you can kind of think of it as sort of one great big huge molecule, all of them all pulling together. They have their own kind of almost a gravity holding it together. There are very, very strong forces holding them together. The next question says a diamond, capital C, carbon, and gold AU are both used frequently in jewellery making, but their properties are very different. Diamond is very hard and can only be scratched by a substance equally as hard as itself. Hard meaning difficult to cut and difficult to use something to deform it, to scratch it. Gold, however, is malleable, meaning that it can be molded into shapes and you can hammer it without it breaking. Ductile, meaning that you can sort of roll it and extend it out, and a bit like blue tack. You kind of roll blue tack or chewing gum, bubble gum, you can pull it into long tubes, and are used for intricate shapes and patterns. So all of this you should know. Explain how the structure and bonding of each substance results in the properties. So these are not in the exam paper, but they're things that I went and got because it's worth looking at them. So this is from Cambridge University and the Royal Society of Chemistry. So this is a diamond. A diamond is really just carbon, but it's carbon in a special shape. So each of these are carbon atoms, and a diamond is an allotrope of carbon. So we see here that each carbon atom is covalently bonded to 4 of its neighbors, and it makes a sort of an extended tetrahedral arrangement. It's this the whole way through. So all of these bonds kind of all reinforce each other, a little bit like the salt bonds in this enormous 3D lattice. These are directional covalent bonds, so these are going in one direction, so they're all pulling in the same direction, and it's a rigid lattice. So you would need an enormous amount of energy, either thermal energy or kinetic energy, to break this apart. That's why it is so strong. It is very difficult to break these. They really, not only do they want to stick together, they really want to stick in this shape. And it's one of the reasons why diamonds are forever. By the way, diamond we used to say was the hardest substance known. It's there's been some substances that have been either created or discovered that are harder than it, but it's still right up there. So let's compare this to gold. So gold is a cuboid crystalline structure. It uses metallic bonding though, where this uses covalent bonding, which is less powerful. It also means that there is this sort of this sea of electrons that are free to sort of basically fly or swim wherever they want between them. And when we take one part off, it's not really going to change the covalent bonds between these or inside these atoms. It also means that the layers here can kind of slide past each other fairly easily, and that's what makes it malleable. When we hit it, they're just going to move and they're just going to stay where they are. They're not going to want to resist that movement, but they're going to want to stay together, and that's what makes it malleable. What else can we say about this? We can flatten them into really, really thin sheets because they don't have to be in this structure. They can be in whatever sort of cubic state they want. Either they can be in very, very thin layers like Ernest Rutherford used in his gold foil experiment, or they can be in hunks of metal gold bars, which I'm sure you're familiar what they look like. And that's how they work. Maybe the big reason why they are malleable is because these layers can slide past each other. I reviewed this and I realized that I made a slight mistake. That is really, really important. this needs to be a negative number. And the reason it's negative, it tells us that, where does it tell us? Energy is released, which means it's an exothermic reaction. So therefore this needs to be a negative number to show that it's an exothermic reaction and that heat, thermal energy, is leaving the substance as a result of this reaction. I think if you didn't have that, you'd probably get that wrong because they say this for a reason. Sorry about that. So now we have the development of the Haber-Bosch process, shown in the reaction below, is historically significant. If you are preparing for the 2026 or 2027 exam, it really would behoove you to have a look at the Haber process in which ammonia is made. It comes up in several different topics. It's a really, really important reaction and a really, really important process, both for bonding and for equilibrium. So it really would behoove you to know how this one works. So we're told that N2 nitrogen gas plus 3 H2 hydrogen gas is combined with 2 NH3 gas, and the enthalpy of reaction is negative 93 kilojoules per mole, so it's an exothermic reaction. Calculate the average bond energy of this triple nitrogen-nitrogen bond using the average bond energies listed in the table below for this reaction. All right, for this one, we really can use this. In fact, we have to use this one in order to solve it. So we know that the enthalpy of reaction, the change in enthalpy of reaction, is negative 93, and it's already in kilojoules per mole. Kilojoules, it's got to be capital J, isn't it? Little k per mole. And we know that's going to be all of the bond energies broken minus all of the bond energies formed. Okay, let's have a look at what the energies that are broken are. So there's going to be one of those. There's a 1 in front of that N2. So it's going to be 1 times the energy from this N bond, plus there's going to be, how many of there? There's going to be 3 of the H bond, which is that one there, minus now all of the bonds that are formed are just going to be 6 of these NH3 bonds, aren't they? So there's going to be, each of them has 3, so it's NH3, but then there's 2 of those, so there's going to be 6 times the NH bond formed. So for every 1 mole of that, 3 moles of that, we get 2 moles of this, and there's 3 of those, so there must be, there's 1, 2, 3 of those bonds there, and there's 2 of them. So there's 3 of these, and there is 1 of those. So these are the bonds that are broken, and these are the bonds that are formed. Right, so now that we have that, we are wanting to find how much energy is required to break up that triple nitrogen-nitrogen bond. So let's, that one there, and there's 1 of them, plus 3 times the HH is 436 minus, and there are 6 of these NH bonds formed, and that's going to be equal to negative 93.0, and these are all in kilojoules per mole, so they're all in the same units there, so we're okay. So let's work them out individually. So 3 times 436 is 1308 minus 6 times 391, 2346, and that's going to be equal to negative 93. Yes, 93.0 if we really want to be specific. Okay, let's work these out. So 1308 minus 2346 is minus 1038. Minus 1038 equals minus 93.0. So this n dash 3 is going to be equal to minus 93 plus 1038, and that's going to be 1038 minus 93 is 945 kilojoules per mole, and that's the answer. All right, we're up to question 2 now. So they want you to identify whether the statements apply to endothermic, meaning that the system takes in energy, namely thermal energy from the surroundings, or exothermic, meaning that the heat exits the reaction. Circling each term correctly. So the first one is the products have more energy than the reactants. So if the products have more energy than the reactants, then it must have taken energy from somewhere, and it must have taken it from outside, so by definition it is endothermic. Energy is released to the surroundings, by definition that's exothermic, and the change in enthalpy for the reaction is positive. That means it's endothermic. This one and this one are kind of the same thing, reworded. That's a really, really easy question. That's kind of insultingly easy question. So state whether the following process is endothermic or exothermic, and give a reason for your choice. So it's H2O gas into H2O liquid. So this is condensation, and condensation is an exothermic reaction. It's not a chemical reaction though, because it doesn't involve the breaking or making of bonds. It is a physical process. So this is exothermic, and the reason that it is exothermic is that the gas has kind of think of the molecules of water as atoms. Here the gases are apart, and here they're fused together. So the gas has more energy. It has more kinetic energy than the liquid. The gases are kind of all over the place. Here, if we imagine these are the water molecules, whereas when it's liquid, they're more closely packed. They have less energy to travel. These ones are just jumping around all over the place in a sort of quasi-random manner. So it needs to release energy to go to this less energetic state. That will be the answer. So gas has less energy. Gas has more energy than a liquid. It needs to lose this, and the only way to lose this is through heat exchange. This is a really, really important process. It's used a lot in industry. If you see the cooling towers, you don't get them so much in New Zealand, but overseas you definitely get these cooling towers that kind of look like that. Those are not nuclear reactors, they are cooling towers. And what it does, they have steam at the bottom here. It rises and it condenses and goes to the bottom. They're actually really, really clever engineering there. And then, of course, some steam will escape out the top, but the main point is to cool the water that's being used in the reaction. So now we're told that ammonium nitrate, NH4NO3, is used to treat first aid and treat injuries. The energy change in the reaction is shown in the diagram below. I think this is the magic spray that they have. You spray it on an injury and it cools it down. So here we have the energy and the reaction process. Is the reaction in the graph absorbing energy from the surroundings or releasing energy to the surroundings? Wow, these are really easy questions. So it's absorbing energy. So you spray it on your injury and it kind of sucks the heat out of the injury. The reason you can tell here is the reactant has less energy than the product. And the only way you can get it is from outside the reaction. So it's endothermic. So for this, the energy is going up in the reaction, so it's positive. Again, really easy questions. You should zip through these. So now we're given 3 compounds, each with polar bonds, but only 2 of them are polar molecules. Define what makes a chemical bond polar and give an example from one of the above. So a polar bond is a type of covalent bond. So covalent bond in which the electrons are not distributed evenly. So what does that mean? It means that one of the atoms, one of the sides of the atoms, one of the atoms is more electro than the other. Okay, so electronegativity, remember the symbol for that. That's the positive side because there is a positive symbol there, and that side points to the electronegative side. So what are some of the examples here? Let's have a look at the water. So H, well, the way they've got it there, it's supposed to be like that, but that's how they've got it. The oxygen is quite a lot more electronegative. So this is electronegative, and the hydrogens are both positive. It kind of doesn't show it there, but so this end is going to be, sorry, that end is going to be electronegative, that end is going to be less electronegative, so the molecule is going to look like that when we do it. Let's have a look at the chlorine, the tetrachloromethane here. The chlorine is, well, let's look at the Cl bond. Chlorine is quite a bit more electronegative than carbon, so that bond is going to be electronegative, but the molecule itself is not going to be electronegative. I think that's probably the next question. And sure enough, here the question is that they want us to circle the compound in the table that is a non-polar molecule. So I guess let's do it here. So it's going to be that one there. Use your understanding of structure and bonding to justify your choice. Well, the carbon to chloride bonds, this is again a lot more electronegative, the chlorine, but it's symmetrical. It's symmetrical, so the geometry of the molecule makes it non-polar. So even though each of these bonds here are polar, the thing itself is tetrahedral, meaning that it might be really negative here and negative, but it's negative here, and it might be electronegative here, but it's also sort of balancing that out. It's electronegative here. So you can't really say that there is a dipole. There is no overall dipole. The individual bonds, sure, but the molecule itself, no, it's not a polar molecule. The next we're asked to predict the solubility, that is, how readily something can dissociate or dissolve into solutes into a solvent. It's the correct column for each combination. Tetrachloromethane, CCl4 and water, H2O. Will that dissolve? And the answer would be no, that would not dissolve. The reason it doesn't is that it's not like, you have to remember, like dissolves like. As long as you remember this, you can't really go wrong. So tetrachloro, what's it, is a non-polar molecule. We've already got that. And H2O is a covalent polar molecule. Therefore, they're not going to dissolve into each other, or tetrachloromethane is not going to dissolve into water. Magnesium bromide into hexane, no, that wouldn't dissolve either. Magnesium bromide is ionic, and hexane is a non-polar covalent molecule. So those are different types of molecules, so they're not going to dissolve. Okay, bromine and hexane. So hexane is, we've already established, that's a non-polar. Bromine is going to be non-polar as well, isn't it? Because it's just two. It's just probably more than one bond there. That is going to be similar. So yeah, bromine will dissolve into hexane, I'd say. So what makes sodium chloride, aka salt, soluble in water? Table salt soluble in water, but iodine insoluble in water. Well, the same reason as above. So what's going to happen when we add salt to water? Well, table salt to water, this is going to dissociate and pair up to its polar opposite. So we've got the Na is going to be positively charged, and the chlorine is going to be negatively charged, and the water molecules, and I never remember which one is which. One of them is going to be closer to the oxygen, and these ones are going to be closer to the hydrogen. I'm just going to check. I can never remember which one is which. It turns out the oxygen is negatively charged. It's going to sort of look like this. So the chlorine here, which are always negatively charged, are going to become attracted to the hydrogens, which are positively charged, and the oxygen, which is negatively charged, is going to become attracted to the sodium ion. So this is the cation, this is the anion. Remember, cations are positive, and this kind of looks like a little cat as well. That's how they're going to do that. Iodine is non-polar. It's just a diatomic molecule, so it's just going to be iodine. Iodine, it's probably not a single bond, but you get the picture. There's no electronegative end, and that's why. I included diagrams showing the dissolving. Oh, okay, I didn't read that, but so I cut and pasted one. Explain how the substance interacts with water molecules. Done that. So these are not going to associate. There's no positive or negative end. It's not like with like, and that's how you probably answer that question. All right, on to question 3. So different forms allotropes of carbon. So allotropes are the same base element, but in a different geometry. They have different electrical conductivities. Diamond does not conduct electricity, but graphite is a very good electrical conductor. It is a very good electrical conductor. Compare and contrast the structure and bonding of these two carbon compounds. Explain the structure and bonding of diamond and graphite. Define electrical conductivity in metals. Justify the difference in electrical conductivity using diamond and graphite. So these are a couple of diagrams that I took from the Royal Society of Chemistry. So on the left here is a diamond. So as we said before, this is a tetra covalent lattice structure. It's a 3D structure. Every carbon is joined to 1, 2, 3, 4 others. What does that mean? It means that there are no free electrons. There's no free electrons. These electrons cannot just roam anywhere. They're locked in there good and proper, and it keeps the whole thing together really, really rigidly. But it means because there's no free electrons, you can't conduct electricity. Electricity is the movement of electrons. So if you can't move these electrons, you can't conduct electricity. The electrons cannot flow through because they're bound to these bonds. Let's look at graphite though. It has this sort of honeycomb hexagonal layer, and they're bound together by van der Waals forces. Each carbon atom has 1, 2, 3 neighbors. So there is one free electron for every atom, for every carbon atom. And that free electron can move. And when it can move, you can create a voltage, a difference in charge possibility, charge potential, I should say, and it's going to flow. It's going to create a current. So carbon, remember, carbon has 4 valence electrons. All 4 are used in diamonds. Only 3 are used in graphite and graphene, and the other one is free to go where it wants. And when it's free to go where it wants, electricity will flow through it. What do they ask? Explain the structure and bonding of graphite, diamond and graphite. Yep, 4 single bonds, 3 single bonds. Define the electrical conductivity in solids. Done that. Justify the difference in electrical conductivity between diamond and graphite. Graphite is a insulator actually, and graphite would be a conductor. So, and this would be a conductor. By the way, graphite is what's in your pencil if you use a pencil, not lead. Next we're asked about combustion. Combustion is a chemical reaction in which a substance combines with oxygen and produces heat. So essentially we burn something in excess oxygen, where normally we give it lots and lots of excess oxygen and we just light that sucker on fire. When ethanol C2H5OH is combusted with oxygen, carbon dioxide and water, like most combustion, is produced. The enthalpy change is negative 1370, so it gives out 1370 kilojoules per mole. Calculate the mass of ethanol that must react to release 17,500 kilojoules of energy. So we're going to presume that it's an efficient combustion. So what do we have to do first? We have to work out how many moles of energy we need to get 17,500 kilojoules. And we're told here that burning it will release, that's what the negative bit means, 1370. So it's going to be the divided by, no, it's going to be the energy released, the energy required, I guess we could say, the energy that we need, divided by the change in enthalpy of the reaction. I guess you could say that we would take the absolute value of that. So that's going to be 17,500 divided by 1,370. The negative bit just means it releases it. And now we grab our calculator. So 17,500 divided by, what was it, 1,370 equals 12.7737 moles. That's how much we need, but the question doesn't ask that. It says calculate the mass, and they generally mean the regular physical mass of something, not the molar mass. But we are given the molar mass, and for that we can use our formula sheet, which is given. Place that. So N is the physical mass over the molar mass, and we want the physical mass, so we need to rearrange it. So the regular mass is going to be just multiplied together, N times big M, and the molar mass is given here as 46.7 grams per mole. And we know that there are 12.7737 moles which are burned up in our ideal combustion reaction, times 46.7 grams per mole, and they're all in SI units, so that's good. So Mr. Calculator comes out, it's already there, so times that by 46.7. So 596.5328, and that's going to be grams. Now they don't really want it in that much unit. It looks like they're just using 3 significant figures here for all of these. So that's going to be 597 grams. Very significant figures. Continuing on with the thermochemical calculations here, we're told that to calculate the energy change when 187 grams of zinc oxide, Zn2, is produced in the reaction below between zinc and oxygen gas. So it's another combustion reaction. So 2 zinc solid, O2 gas, 2 zinc oxide solid. Okay. So, okay, maybe it's not a combustion, but similar reaction, and it gives off 696 kilojoules per mole, and the molar mass is 81.4 moles, grams per mole. So what are we actually given? So we're given here the physical mass, and we're given here the molar mass, and we're given here the change, and there are 2 zinc oxide produced. So how many moles of zinc oxide are actually produced? So that's going to be, how are we going to work that out? That's going to be the physical mass over big M. So that's going to be 187 divided by 81.4 grams per mole. So the grams bit will cancel, and we're going to be left with the number of moles. All right. So 187 divided by 81.4 is going to be this nasty number, 2.297, 2.297 forever. Okay, so that's going to be how many moles are produced. And what are we told then? So we're told that this is the total amount of energy that's released, but that's 2 moles. So we need the kind of the enthalpy change released per mole. So it's going to, so that's going to be this number here, negative 696 kilojoules per mole, divided by 2, because there are 2 moles that are being created here. Okay, Mr. Calculator comes out again. So let's just ignore the minus bit. That just says that it's releasing in an exothermic reaction. So 348 kilojoules per mole. So I guess we could say it releases 348 kilojoules per mole. And there are this many moles. Each mole will release this. And what are we actually asking? Calculate the energy change. What are we actually trying to find here? Okay, so I think I know what they're trying to say here. This is an ideal reaction here. So if we have 2 moles of zinc and 2 moles of O2, we would produce 2 moles of zinc oxide, and it would release that much energy. But we don't have that. We have 2.29 moles that are produced, not 2. So it's going to be a little bit more than that. And it produces 348 kilojoules per mole. So the total energy, I guess the total energy released is going to be the number of moles times the energy per mole. Again, we're sort of presuming that there is 100% yield and it's a perfect reaction. So that's going to be 2.297 times negative 348 kilojoules per mole. And the moles are going to cancel. So 2.297 times 348. It's going to be negative 348. So 799.356 kilojoules. And these are all in 3 significant figures. So that's going to be 800 kilojoules. 3 significant figures. So I guess the bit that would sort of trip me up, I hate to sort of read it really, really carefully there. This is an ideal equation. And we, introduced this amount. So it wasn't two. If we just had 2 moles of zinc, 1 mole of oxygen gas, we would make 2 moles of zinc oxide. But we didn't create 2 moles, we created 2.29 moles. So it's going to be a little bit more than twice this. So now we're asked to draw a Lewis structure, electron dot diagram, in case you didn't know what a Lewis structure is, for each of the following molecules and give their shapes. So maybe good practice for drawing a Lewis diagram. So let's do CO2 first, carbon dioxide. Okay, we'll go into our tables. And pull this information up. So we've got carbon and oxygen. So let's look at how many valence electrons are in the valence shell. So here it's full. So there's 8 here, 7 here, 6, 5, and 4. So carbon has 4 electrons in its outer shell, so it needs 8, so it needs 4. Oxygen has 6 in its valence shell, so it needs 2 for each. So what have we got? We've got a carbon and oxygen, so the carbon is going to be in the middle, and let's have the 2 oxygen to one side, and we'll give them 1 bond for now. So that's the minimum shape that carbon dioxide would have. So now let's look at how many electrons are free. So carbon has 4 and it wants 4, so there are 2 here, 2 here, so it's all 4 of its electrons are in these bonds, so it still wants 4 more. These oxygen, they've got 6 and 2 of them are there, so they've got 4 spare ones. Do they? No, they don't. So this carbon wants 4 more. These have got 6 already. 2 are accounted for, so they've got 4 electrons left over, and it's going to be like that. So if we give this one another bond, that it will lose that one, and this one will have 2, 4, 6, and now it has 8, and it loses that one. So each of these oxygen now is 1, 2, 3, 4, 5, 6, 7. And let's have some practice doing Lewis structures. So we're told these 3 structures here, the Lewis structure, then the name of the shape. So let's do some practice. So carbon dioxide, CO2. Let's have a look at the atoms themselves. So these have 8, 7, 6, 5, 4, and 3 in the valence shell. They all want 8, so carbon is here. So carbon has 4 and it wants 4. Oxygen is here, so it has 6, so each of these it wants 2. Okay, so which is going to be the central atom? It's going to be carbon, and the 2 oxygens here. So the simplest form of this molecule would be that if we give it a single bond. So what is going on here with the carbon? The carbon has 4, so all of the carbons are used, but it still wants 4 more. And here the oxygen, only 2 are used up, so it's got 4 spare ones, and this one must also have 4 spare ones. Let's do another bond here. This oxygen now is 4 of them are used up. It has, so 4 of them are used up here, and it has given 2, so it's got 4 along the outside here. The carbon, it has 6 now. All of its own electrons are used up, so it wants 2 more. So let's do another one there. Now the carbon is happy. The oxygen here, 4 are used, and it has 4 of its own left, so it's going to be happy. So this is our final structure. So we're going to have carbon, oxygen. There's no valence here. There's 2 here, 2 here, however you want to do that. So the name of that shape is going to be linear. And here is what carbon dioxide is going to look like. Clearly linear. Next, let's look at the, what would that be? The chlorine monoxide, I guess. Okay, so let's find chlorine. So chlorine is got 7. It's got 7. It wants 1. And there are 2 of them. And the oxygen here, it's got 6. It wants 2, and there is 1 of them. So let's look at what we've got. So how many electrons have we got, and how many do we want? So we've got 2 times 7 plus 1 times 6. It's got 14. We've got 20 electrons in the valence shell, and we want 2 plus 2, we want 4. So we've got to make some of these electrons do a double shift. Okay. What's going to be the central atom? The central atom is going to be the oxygen, and let's give it the most basic shape here. So the chlorine here, it picks up an electron from the oxygen. So it had 7, it's got 1 now, it's happy. This one's happy. The chlorine here is going to be in the same boat. It started with 7, it's picked up 1, so that's going to be mostly happy. The oxygen started with 6, it's picked up 1 here and 1 here, so it's got 8. So the oxygen is going to be happy. So we're happy all round. Okay. So these are going to be single bonds. So the chlorine and the oxygen and the chlorine. So there's going to be 1 to 1 to 1. So 2, 4, 1, 2, but it's not going to look like that. And these have got 6 to make up, however you want to put them in. 2, 3, 4, 5, 6, 7, 8 happy. 1, 2, 3, 4, 5, 6, 7, 8 happy. 2, 3, 4, 5, 6, 7, 8 happy. So now what do we need to do? We need to work out the shape of these things. So let's kind of do the, okay, what's the shape going to be? Well, we really have to go to VSEPR for this. And this is going to be polar. These are more electronegative, so this is going to bend it. So it's going to be, this is going to be bent, isn't it? It's going to be planar bent. Okay, next one. So here's what this is going to look like. Let's animate it, and it is indeed going to be bent. Lewis diagram wouldn't really tell you that it was bent. You'd really need to use VSEPR theory to know how bent and the final shape. It kind of looks like a poodle, I guess. Last one up is the boron trifluoride. What is this one going to look like? So let's have a look at this. So boron has 3, and there is 1 of them. Now, does it want 8? Boron is a kind of odd one out. It's cool with 8, but it's also cool with 6. So I have a feeling that could come back and help us. The fluoride here is 7. It has 7, so it wants 1. And there are 3 of them. So we have 3 times 7 plus 1 times 3. So we've got 24. We are looking for 3 here and 3 or 5, depending on how we go. Let's draw the basic skeleton and see how we go. So the central is going to be this boron, and there's going to be 3 fluorides coming off it. Now each of these fluorines now is happy because it started with 7. It's picked 1 up from boron, so this one is happy. This one is in the same boat. That's happy as well. This is happy. Now, is the boron happy? Yeah, it is. It's not going to get any more electrons, but it is happy with 6. So this is kind of happy here with 6. So this is our final structure. So the boron has no dots around it, and these fluorines will have 3 lots of 3. So it's going to be boron 2, 3, 1, 2, 3, 1, 2, 3, and this is going to be trigonal planar. But yeah, remembering that boron is happy with 6, it's kind of the odd one out. It's not happy, but it's stable with 6 valence. The last question asks us to comment on the difference between the shape of methane and ammonia. So they are quite similar beasts in that they have a central atom that is it has a pyramid beneath it. If you sort of look, this bit here is kind of the same bit, but it has this kind of extra hydrogen out the front here, on top. So why the difference? Well, the difference has to do with VSEPR. So VSEPR is a valence shell electron pair repulsion analysis. All right, so that tells us pretty much everything that we can need to know at this level anyway about the shape of these molecules. So methane here, the central atom is the carbon atom, and a carbon atom has 4 steric, has a steric number of 4. And what that essentially means is that this is the sum of the lone pairs and the bonded atoms that are bonded covalently through their electrons. So why does methane have one more than ammonia? The long and short, the quick and dirty answer is that here is carbon here. Carbon has, see, neon has 8, fluorine has 7, oxygen has 6 in its valence shell, neon has 5, nitrogen has 5, and carbon has 4. So it wants 4, and it's going to get it from these hydrogen, essentially. And there are sort of 4, the steric number for both of these is in fact 4. So when the central atom has a steric of 4 like that, you're probably going to get that basic triangular shape, that pyramidal shape at the bottom here. So tetrahedral is kind of the same as trigonal pyramidal, and then it has this kind of antenna out the top here. So this extra hydrogen out the top here is ensuring that this carbon has a full octet. Hydrogen, of course, only really needs one electron, and it's quite happy to share it with the carbon and the nitrogen. So the nitrogen has one more electron in its valence shell, but has the same steric number. So it's going to have that same shape here, but it doesn't need that antenna out the top. It's quite happy. It's got its octet. So why that shape? So that shape maximizes the geometric distance between the charges, the like charges. So the first thing we would do for VSEPR is we would work out how many nodes there are. Nodes are places where you can put electrons. They both have 4, but the makeup of lone pairs of electrons is different from ammonia and methane, and carbon is a little bit more greedy. It's a little bit more to the left here than nitrogen, so it wants that extra electron that the hydrogen can give it. And that's pretty much the difference. There is here a little thing that I think methane is a little bit out, and I don't think it is 109 degrees. I think it's, from memory, it's like 107.5 degrees. It's something really, really close, but the change difference there by VSEPR is slightly different, but essentially, yeah, that same shape, but with an aerial. So that's the end of the exam. So this is a mixed bag exam. Some of the questions are really, really, really easy. Some of them required you to know a little bit of valence and VSEPR theory. So slightly strange exam, but no, an enjoyable exam anyway. So that's that.